In the previous video in this build series, I had a look at the pitch bend system that I built for the electronic valve instrument I'm building. As I explained, the vibrato system is a slightly different thing. It's for small variations in the pitch or character of the note being played, rather than for large shifts of up to an octave in either direction. To build this part of the EVI, I was originally planning to use a joystick from a PSP, or PlayStation Portable. These are really cheap and they can also sense in two directions, which I thought would be a pretty cool option for adding another dimension of control to the final instrument. I started wiring up the joystick to see what the characteristics were like, such as if it was linear. In short, I ended up pulling off some of the copper trace on the fragile PCB by accident, and after some semi-successful attempts at trying to fix it, I ditched the idea and turned to using a Hall effect sensor instead. I had a few of these laying around, and I thought they were a cool alternative, and something new to try. Hall effect sensors can sense the intensity of a magnetic field by exploiting the effects of the Lorentz force, and are found in numerous applications, often where position sensing is required, like in crankshaft rotation sensors and linear encoders. If you want details on how they work, check out my video on the topic linked in the description. What I'm showing you here is how the output voltage of the sensor changes depending on the strength and direction of the magnetic field. By wiggling the magnet further and closer, I can get an oscillating signal which I can put to use to control my instrument's pitch. Before this signal is used, however, it needs a little bit of processing to make it suitable for my application. To do this processing, I've designed and constructed a simple filter. In electronics, a filter is simply a circuit or even a digital system that takes some input signal and performs a transformation on it to produce some new signal. This is the circuit I came up with in the end, after a little bit of thinking. It's broken into a few different stages which all perform slightly different purposes, culminating in the overall effect I'm aiming for. This is something that's handy about filters in general. You can chain them one after another, and their effects stack. First up in my system is the Hall effect sensor itself. I'm using the A1301 EUA-T. I bought these in 2015, back in the pre-apocalypse era, and as you can see from the datasheet, they don't actually make this model anymore. There are oodles of alternatives to this thing though, so if you're thinking of making something with a Hall effect sensor, please don't let it deter you. This capacitor up at the top in the circuit is called a decoupling capacitor, and is used to prevent noise from the power supply from getting into the sensor's signals. These are found in basically any circuit where you have sensitive chips, either as protection for the chip itself, or to keep signals nice and clean. Next up we have a few resistors and a second capacitor that together make up a DC blocker, also known as a high-pass filter. As the name suggests, this blocks the DC offset in the output from the sensor. If you were speedy in reading the datasheet, you might have seen mention of quiescent voltage. This is that DC offset I just mentioned. The two resistors in my high pass also have the effect of shifting the DC operating point to where I want it. This is required as the sensor outputs a range of 0 to 5 volts, while my teensy microcontroller can only take a range of 0 to 3.3. What I'm doing here is stripping off the 2.5 volt quiescent voltage of the sensor, then recentering it in the middle of the 3.3 volt range of the teensy. Another thing the high pass filter does is remove any offset caused by leaving the vibrato lever in one position. This might happen if you're holding the instrument badly, or if the lever is not correctly returning to the exact same position every time it's released. I'll show you what the effect of this sounds like later, but to put it simply, it causes the pitch to slide back into the center itself after a short transition time. Once I've set the DC point, I need to shrink or attenuate the signal. This is to fit the signal, which would still have a magnitude of 5 volts down so that it's at most only 3.3 volts. I do this with a pair of resistors that form a potential divider. Those two resistors also form part of a low-pass filter. This is to prevent any high-frequency noise from the sensor reaching the teensy, and also to damp any voltage spikes caused by quick changes in the magnet's position from damaging the teensy. It's a little harder to draw, and this is not 100% accurate, but it should give you an impression of the effect. Finally, there's a Schottky diode to block any reverse current that may result from a reverse voltage slipping through the rest of the filter. While this is a pretty simple circuit, I'm also pushing 99% sure that it's not the best way to do this. For example, some of the resistors could be omitted, I think, to make it a bit more efficient, and the diode might not be strictly necessary. Saying that though, it works out as I want it to, so there's really no biggie. Most of these components are also dirt cheap, and if you're lucky you can even sometimes get them included as freebies in kids' breakfast cereal packets. Now that we've covered what the actual circuit is doing, I can give you a little demo of what this thing might sound like in use. The synthesizer I'm using here again is the free software called Sunvox, and as always I'll pop a link in the description of this video to it. As I wiggle my finger on the little vibrato lever, I can alter the pitch slightly, as you can hear. This is pretty responsive and lets you do traditional sounding vibrato like this. It also lets you do some more interesting stuff like these kind of sweeping notes. These sweeps are caused by the high-pass filter returning the voltage back to the center point. This is an important feature as it will keep the pitch from straying if the lever doesn't center itself perfectly. The additional ability to add these sweeping notes is just a bonus side effect in my opinion. By tweaking the software parameters, the vibrato could be made to be very soft or also very violent. Because your finger controls every little pitch alteration, this has potential to be way more expressive than the common synthesizer vibrato, which is likely to be either fixed speed or amplitude, or be generated according to a mathematical equation. The mechanical parts of this are pretty simple. It's basically just an M3 bolt with a little thumb pad at the top and a magnet holder at the bottom. The magnet needs to be held at just the right distance from the sensor so that it can output the full range of voltages without clipping at either end. The screw thread makes this spacing a bit easier to adjust. The little rubber donut that I'm using as a soft sort of spring to hold the lever is a vibration damping washer from a DVD drive. If you've ever wondered what's inside a disk drive, now's your chance to see. This squishy thing I'm poking at is one of the vibration mounts that I'm talking about. You can also see the carriage that holds the optical system that reads the patterns in the surface of the disc here. If you've seen my pitch bend video, you'll remember that the pitch bend pad positions are adjustable, and this is why. Your thumb needs to fit between the pads with a little bit of clearance on either side, so you don't accidentally whammy bar while trying to gently add some vibrato. This mechanism was the result of a sort of circular design process, where I did a full turn after ambling through a pile of other designs. After several evenings of CAD work and going through some designs like this one, which I thought looked cool, but in practice just didn't really work out, I settled back on the wiggly stick idea that I had started off with. Maybe this is a lesson in simplicity, often being the best solution. Well, that pretty much sums up the vibrato system. I'll leave you with some funny noises I discovered while playing around with this in the pitch bend system. I think I've actually worked out how to make R2-D2 sounds if I ever need to. As always, I hope you enjoyed the video and learnt something. If you like, please drop a like, and maybe leave a comment even. I've been really enjoying replying to the few comments I've gotten so far, and I hope that continues. Until the next time, stay safe and have a great day.